the webinar will be meshing hacks in simulation. It's okay. You can listen to me first. Okay, now we will start but not sure we will. Okay, thanks. Okay, now let me show the agenda of this webinar first. So the webinar it is for the simulation who have simulation experience or who want to learn some simulation method. Okay, so the first topic in my webinar will be the mesh type of element and type of mesh you use in SolidWorks simulation. Okay, then the mesh quality. So as we all know that if we want to do a simulation, the mesh is a very critical section of the project, right? The more accurate of the mesh, the more accurate result that you can get. So the mesh quality, we will use the aspect ratio and Jacobian plot to evaluate the quality of the mesh. Okay. Then the third topic will be the mesh refinement. How to refine your mesh at a location of your interest. We will use the mesh control to refine the mesh at the specific location in your geometry. Okay. Then the last section will be the question and answering. We will also have a small quiz after the webinar. The question of the quiz is from my slides. Okay. So before we start the first topic, I would like to show the overview of the simulation process, a basic review of the simulation process. So if I think all of you are SolidWorks user, right? So if you're a SolidWorks user, then you should have the experience to design a geometry in SolidWorks and more features like the fillet, the chamfer, right? So for the small features, the fillet and chamfer, actually the small features will not affect much of your result during the simulation. So and it will consume a lot of computational resources. So the first thing, if you want to do the simulation, is to simplify the geometry. Simplify this geometry. So this is the first step, the idealization of the geometry. Okay, then after that, we can start to do the finite animal analysis pre-processing. Okay, let me see what is the message in the chat box. Hi, can you share the PowerPoint after the session? Okay, sure, of course. Thanks. Okay, then the next step is the pre-processing, which is the apply the boundary conditions, apply the property, apply the material to the solid bodies. So you can see we need to this one I admit the person. Okay. Define the type of the analysis first. What kind of analysis you want to do? The structural static analysis, or structural dynamic analysis, or the frequency analysis, or the buckling analysis. So that is the first thing. You need to define the type of what kind of analysis that you want to do. Okay. Then the next is the material properties. So for every solid body for the simulation, we need to assign a material to the solid body. Solid simulation has a very strong material database. Then the next thing is the support, which is the restraint. Apply the boundaries to the geometry, and then apply the external load to the geometry. So all of this so-called is the mathematic model. We will use those kind of properties to establish the formula, which is the mathematic model. Okay. Then after we have applied the boundary conditions, we have established the mathematical. The next convert the mathematical model model in a model. This is what we want to introduce in our webinar, how to ensure the quality of the mesh for the geometry. Then the next thing is the solver. Then can run after you have the FEA model. Then can run the simulation. Okay. Then can do the post processing. What kind of result you want to get? You want the maximum 1 meter stress plot, or the displacement plot, or the strain or stress plot. What kind of plot that you want? So that is the let me minimize this. That is the post processing so-called. Okay. And I will move to the next slide. So in SOLIDWORKS simulation, there are 3 types of element. A solid element for 3D model. If you have a 3D model, then you can consider to use the solid element, right? Shape element, which is the shape element, which is a 2D mesh. This one, in SOLIDWORKS, the shape method, which is the thin plate. You can see this one, the thin plate. It will be converted to shape element automatically in SOLIDWORKS. Okay, the shape element is actually a 2D element. You can see this is a triangle. This is first order. This is first order shape element. This is a triangle. And then the right side, this one is the second order. The second order is one more point here. You can see the display, the stress strain relation is not linear with each other. So this is the second order. Okay. Then the last one is the 1D beam, 1D mesh beam element. You can see this is the beam element. Use a 1D segment, this one, to represent declinize the 3D model. Okay, so this is the 3 types of element in SOLIDWORKS. We only have tetrahedral for solid element, and then triangle, this triangle for the shape element. Okay. Then the next thing is the types of mesh parameters. So in SOLIDWORKS simulation, we have 3 types of mesh parameters. If you want to create mesh for the geometry, then you should notice that under the parameters, you have 3 options. Okay, the standard mesh and the curvature-based mesh, and then the blended curvature-based mesh. So which one should we use? That is a very important question, right? Which one should we use? For standard mesh, this is first standard mesh. This is first developed in SOLIDWORKS simulation, which means the first time when the developed team develop this software, then this is the only mesh that you can use, the standard mesh. Okay, for the standard mesh, the element size, you can see this image. The element size is almost the same within the tolerance. You can give assign define an element size for the element for the triangle here, and then you also can give a tolerance to the size of the element. So the element size is almost the same with tolerance. This is constant size or constant size. Then after that, we found that standard size actually cannot satisfy what we want, cannot help us to get accurate result. That accurate result. So and we then the curvature-based mesh, this one, then the curvature mesh. This is the variable element size. Variable element size. You can specify a maximum. This is the maximum element size, and then the minimum element size. The element the element size will between the minimum and maximum, especially at the small features in the geometry. So for example, the small features in the geometry will use a smaller element size, right? Smaller element size. This will help the users to get more accurate result. This is the main purpose of this map. So usually if you want to get a more accurate result, then you should choose this one, curvature based mesh. Okay, then how about the blended curvature based mesh? Because sometimes if you use the curvature based mesh, if your geometry is very complex, then sometimes it will fail to create the mesh because of the large aspect ratio, because of the large torsion of the geometry. So in this condition, the blend curvature based mesh can help you resolve the failure from the curvature based mesh. So in this condition, you should use the blended curvature based mesh. If it fails, if you use the curvature based mesh, then you can move to the next one, the blended curvature based mesh. Okay. Let me show this in SolidWorks. Can see my screen, right? Okay, see this one, I have set up the simulation. Then the fixture I have add, the external first I have add. Okay, then the mesh. Now I create a mesh. If I right click and then create a mesh, this one. Okay. Okay, then check the mesh parameters. So you can see there are three options. The standard mesh, you just need to give a global size, which will be used for the global element in this geometry, and then a small tolerance. Okay, this is the standard mesh. I create the standard mesh first. Okay, so you can see the mesh, the size of the element is almost the same. Okay, then let me right click the mesh again and then recreate the mesh. Now I use the curvature based mesh. So the first one can assign the maximum element size and then the minimum element size. Now for the minimum element size, let me change this to 10. Right? So this and then I click to create the mesh. It's very big. Okay, so now you can see what is the difference. You will find that the mesh, the element is different in different location. The element size is different, it's variable. It's not that constant. Curvature based mesh. And then the next one is the blended curvature based mesh. This one, if you use the curvature based mesh and then it fails to create a mesh, then you can consider to use the blended curvature based mesh. So this is in which type of mesh parameters should you use when you do your simulation? Okay. Okay, so this is the types of mesh parameters. Okay, now we move to the next, the shell element idealization. So sometimes we need to use the shell element, but why should we? What is the shell element? It is actually a 2D. It is a surface element. It is a surface mesh. And then why should we use the shell element? So and we say if for example for this one, if we use the solid element, this one we can use the solid element. If we use the solid element, then I say that it will take 2 days to finish this simulation, to finish this job, okay, to run this simulation. But it will take only 2 hours to finish this simulation if I use the shell element. Which one should we choose? And then the result is quite similar. The result is quite similar. So of course we should choose the shell element, right? Because it can save a lot of computational resources and time. So faster calculation and less computational resources consumption is our consideration. And then when should we use the shell element? Not all the conditions can we use the shell element. In SOLIDWORKS, SOLIDWORKS will automatically create the shell element for the sheet metal and surfacing. For sheet metal body, SOLIDWORKS will convert it to shell element automatically. And then for the surface body, the same. SOLIDWORKS will convert it to the shell element automatically. Okay. And then one more thing is to properly use the shell element for the solid body, we need to check the thickness ratio. What is the thickness ratio? If you see here, span to thickness ratio. Thickness ratio is the length over the thickness. If the length of over the thickness. If the length over the thickness is less than 10, then it will be good to use the solid element. It will be good to use the solid element. But if the length over the thickness is more than 10, then it will be better to use the shell element, because the experiment has proved that it is quite similar if you use the shell element and the solid element to run the simulation. Okay. So remember this one. So I have, as I mentioned before, the questions in the quiz is from my slides. Okay. And for if the length over the thickness is over than 10 but less than 20, we will consider it as a thick shell. And then if the length over the thickness is more than 20, then we will consider it as a thin shell. Okay, let me admit one more participant. Okay. Okay. So how can we create the shell element for the geometry? It is also very easy. You just need to right click and go to the shell manager and can assign the shell element for the geometry. Okay. So for example, if I want to use the shell element, but you need to calculate, of course, the length over the thickness is less than 10. So for this part, we should use the solid element. Then let me show one more example. If I create a new part, okay, I create a very thin part. Okay, then create the geometry. This one. Okay, now I create a extrude feature. Then the thickness I give 0.1 inch. Okay, then the length of the rectangle here, I give this one 12, which is more than, okay, this one 10. Okay, so I save to my desktop and then go to the simulation, create a new study here. Static study, define the type of the analysis and click OK. Okay, then let me assign a material to the part first. I give a plain carbon steel. Okay. Okay, then for the fixture and external node, I will not add here. I skip the fixture and external node, go to the mesh first. So if I right click and then create mesh, this will create the solid mesh automatically. So I accept all the default settings. Okay, then create mesh. So this is actually the solid mesh. This is actually the solid mesh. So how can we create the shell mesh for this geometry? So if we right click this solid body, the part one, right? There is a shell manager or define shell by selected face. Okay, now we go to the shell manager and then choose a set face. You can choose the top face, can choose the bottom face, also can choose the middle face. Choose the top face. And then design top surface. The selected material plain carbon steel. Then click OK. So now if we go to the simulation, this is the so-called simulation study tree. You can see the icon here. This is a surface. Now means it is a shell element. It is a shell element. Okay, so if I create mesh, and click OK. Thickness is not defined for the shell, right? So let me define the edit definition and then give a small thickness. The thickness just now is 0.1 inch. Okay, then let me create the mesh. Accept the default settings. I don't need to change the parameters. Okay, so now as you can see, if I zoom into this part, you can see now this is a 2D element, right? This is a triangle 2D element. This is so-called the shell element. See, this is so-called the shell element. So as for the reason why we don't want to use the solid element for this part, because for simple geometry it is still okay, but for the very complex geometry, we can use, of course, we can use the solid element, but it take a very long time to run the simulation, and then the more element we have in the project, the more errors that will be that can occur. So it is better to use the shell element for the sim part. Okay, so this is the shell element. Okay, let me accept this. Okay, so this is the shell element idealization. Understand why we use the shell element, and then when should we use the shell element, and how can we use the shell element? Okay, then move to the next one, the beam element. So for the beam element, it is the 3D wireframe representation of the 3D solid. You can see the image here. This is a structural member here, and then we use the 3D frame to represent the solid, to represent this geometry. This can be extremely fast, and then sometimes it is more accurate for long wireframe geometry. It is more accurate than the solid element for the long wireframe geometry design. And then the reason why we use the beam element, of course, it will be very fast. It will be quite faster than the solid element to run the simulation if the result is similar. Usually in SolidWorks, the structural member, the beam element will be created for the weldment and the structural member. So remember, in what condition should we use the beam element in SolidWorks simulation for the structural member and then the weld method. Okay. So this is the first topic in the webinar. Then we move to the second topic, mesh quality. How can we evaluate the quality of the mesh? I create a mesh, but I'm not sure how to evaluate the quality of the mesh, right? So now I would like to introduce two ways to evaluate the mesh quality. The aspect ratio check and Jacobian check. Aspect ratio check. You can see, this is the two plot. The left side, this image is the aspect ratio plot, and then the right side, this is the Jacobian plot. Okay, let me show. What is the aspect ratio? For the aspect ratio, if you see the image here, the aspect ratio is the A, this value, over B. So the large aspect ratio means the large distortion of the element. If the element has a large distortion, it will create less accurate result. So if it is a very regular element, this one, then the more accurate result that we can get from the simulation. Okay, so this understand what is the aspect ratio in this slides. Okay, so the perfect tetrahedral element aspect ratio is 1. If it is 1, means it is if it is 1, means the 3 lines has the same length of the triangle. So it will be very accurate for the result. And then we still can accommodate a larger aspect ratio value. Aspect ratio value should be kept below 50 in the regions of interest. Should be kept below 50. If it is over 50 in regions of interest, then we will consider that the result will not be that accurate. So this is how you can evaluate the quality of the mesh. Okay, let me show a small videos how to plot the aspect ratio. So in this video, if you right click the mesh and then create the mesh quality plot, okay, and under the display, choose the aspect ratio, you can see, and click OK. You can see the legend, the red color indicate the large aspect ratio, and then the blue color indicate the smaller aspect ratio. The maximum aspect ratio value should be kept below 50 for result accuracy. So you can see in this model, it is very apparent that you can see the maximum aspect ratio in the legend is 3.072. So we can say that the result will be accurate. Okay, so this is one of the method, the aspect ratio plot. Okay, I show this in SolidWorks. If I go to my SolidWorks, SolidWorks, okay, close this. Then for this one, if I right click the result, the mesh, right? If I right click the mesh and then create mesh quality plot, aspect ratio, under the display, you can choose the aspect ratio, choose the Jacobian. We choose the aspect ratio first. Let's see. The red color indicate the higher aspect ratio, and then the blue color indicate the small aspect ratio. And from the geometry, from the graphic view, it is very clear that whether your aspect ratio is large or not. Okay, especially for the complex geometry. Especially for the complex geometry contains a lot of small features. Then you need to be careful of the small features, whether the aspect ratio is okay or not. Okay, then the next one is the Jacobian plot check. Okay, So what is the Jacobian shape? If you see the image in the right side, this is the tetrahedral element in SOLIDWORKS simulation. Okay, then if the tetrahedral is a regular shape, is in the perfect shape, then the Jacobian value is 1, means there is no torsion, there is no distortion of the element, there is no transformation of the element, there is no rotation of the element. So it will be in the perfect shape. So at this condition, the Jacobian value will be 1. If there is any rotation, transformation, or distortion of the tetrahedral element, the Jacobian will be over than 1 or be negative. This you can see the element in the right side, the tetrahedral in the right side has large distortion. So it is far over than 1. It is far over than 1. Okay. So what is the critical value of the Jacobian value? Usually, in general, Jacobian of 40 or less is acceptable. This is acceptable. Of course, the perfect value is 1. And then as the element distort, Jacobian increase or becomes negative. This is defined by the Jacobian formula. The Jacobian formula is a derivative formula. If you are not sure it's the formula, you can search in the Google and then see that this Jacobian value defines the distortion, the rotation, and transformation of the tetrahedral element. Okay, so remember, keep in mind this value. Jacobian of 40 or less is acceptable. Sorry, let me accept this participant. Okay, let me show a small video to see how can we plot this. If you right-click the mesh quality, and then create the mesh quality plot, and then choose the Jacobian ratio, click OK. You can see the blue color indicate the small Jacobian value, and then the red color indicate a larger Jacobian value. So it is quite clear from the graphic view whether the Jacobian ratio is large or not. Okay. So, but remember keep in mind the Jacobian value of 40 is acceptable for the geometry. If it is over, then 40, it can create the mesh and then can run the simulation, but it will cause the less accuracy of the result. Okay. So this is the Jacobian plot. Then the next one, the third topic I want to introduce in this webinar is the mesh refinement, which is the mesh control in SOLIDWORKS simulation. So mesh control, we will use mesh control to refine the mesh in the area of interest in your geometry. So for example, we want for example this L bracket, this geometry, this corner at this corner, right? The stress at this corner is quite strange if you run the simulation. If you don't apply any filler at this edge, it will be very large. It will be very large. So in order to get more accurate result, we apply the mesh control along this edge in order to get more accurate results. Okay. So this left side is the no mesh control and mesh control, and then experiment has proved that the more you refine the mesh, the more accurate result that you can get until the result is converged. So that's why we add the mesh control, and then you should not apply the mesh control to the whole geometry, because if you apply the mesh control to the whole geometry, then the number of the element is quite a lot. So it will take longer time. it will take longer time to run the simulation, and then it will consume a lot of computational resources, and sometimes the simulation can be failed because of large cumulative errors. So this is the mesh control. Apply the mesh control at the location where you're interested. So in this hide my plot. Okay, I hide this plot. So for example, I'm interested at the location at this circle here. So I can right click the mesh and then apply mesh control. You can select the faces, select the edge, select the points, and then the component for mesh control. I select this face. Then the element size, you can give a smaller value. I give 1.5, and then create mesh. So you can see the element size on this cylindrical face is smaller than the element size in other areas in the geometry line. Okay, so this is the mesh control. How can we apply the mesh control? And then why we use the mesh control? Apply the mesh control at the area of interest to get more accurate result. Okay. Mesh refinement. This is the method in SOLIDWORKS simulation to refine your mesh. Okay, so this is the